Okay, so let's look at the Wilcox K omega model. And without getting into the derivation too much, I can just summarize it as follows. The K equation was already formulated, eddy viscosity already formulated, and there's an omega equation which needed modification. And omega equation was formed originally by dimensional analysis, and its major correction was putting it in a form which is sort of consistent with the K equation. So here's our K equation, turbulent kinetic energy. And now we have a specific dissipation rate equation for omega. And you'll notice that there's no power, so it's not an omega squared model, which are maybe second most popular. And so just look at equation 610, which is your second PDE for a two-equation model. And you'll notice really only one thing that's different from Kolmogorov's model, who had no computers, no excellent experimental data. And that's this term. And this is nothing but what we would view as a new term, right? And it's a production type term. What's also interesting about the model is this term here is really exactly the same, and so is the last term, except the closure coefficients. You'll also notice that we're using a K equation instead of like a B equation, which was like that RMS velocity fluctuation equation. So it's only a tiny bit different. And another great thing about the way Wilcox laid out his model, and one of the reason it's so popular is it seems so structured, and there's so much similarity between the two equations. Like you can see on the left-hand side, which is a K and omega, first terms are still partial ui, partial xj, a little bit different coefficients for production. And then you say, okay, well, we have a negative beta omega squared or K omega, and then this last term is exactly the same except for K and omega and different closure coefficients. He also puts a little star in the K equation coefficients. And just to summarize his model, these are the closure coefficients and auxiliary relations for, I think, his 1998 model. So this is one that's probably the most accepted and calibrated. And it's also elegant. And you can see, well, really we only have a few closure coefficients, and here they are, and some auxiliary relations. And you might say, well, this is great, but how do you find these? And I can tell you what's wonderful about this model, inspired by Andrei Kolmogorov's view of homogeneous isotropic turbulence and the theory of boundary layers, is that we don't really need too many experiments whatsoever to come up with these closure coefficients. And if we run this model on a CFD solver, we'll have excellent results for a huge range of compressible boundary layers in equilibrium flow and the flow external to it if it's decaying. And why is that? Because the closure coefficients were done against the theory of homogeneous isotropic turbulence, which is why I mentioned it earlier, and also boundary layer theory for log law. So let's look at how these came about. Oh, and I should also note, this is also a compressible model. And what he did was he formulated it by incompressible flow, and then if you multiply mu and mu t, the viscosity, eddy viscosity by rho, that's one step, and multiplying all the other terms, in the closure, then you'll get a compressible model. So it works for compressible flows too. Now, of course, you'll also need an energy equation and equation of state. So you see, went down the incompressible path and relaxed the compressible assumption, incompressible assumption. So there's lots of notes about these closure coefficients, and some of them become 0. For example, let's see, this one would be 0 for 2D flow. I don't want to spend too much time talking about some of these little reductions and details, but you'll see that this model is excellent predictions of boundary layer flows, and you'll see why in a second. And some of these functions like FB, or F beta star, alpha, beta, all these closure accelerations, in later models, these are calibrated against all kinds of flows like wakes, boundary layer, free shear layers, jets, backward facing steps, and it works really well. So the coefficients here are kind of more theoretical, but what would happen if you're bringing up a contemporary CFD solver is the default coefficients have been likely calibrated across a whole range of flows. And the problem with that is then you really kind of have more of an empirical set of coefficients that aren't based in like physics of one particular flow. So you can always get a better prediction likely if you use coefficients that have been calibrated for one particular flow. So just be aware of that when looking at these types of models. Altogether, in general, for K omega models in this Wilcox general form, which is like its standard form, you have to find 11 coefficients and 2 auxiliary relations or functions. That's the minimum. You can always turn some of these things into functions, like they do in a lot of algebraic models. So let's talk about the closure strategy of Wilcox. So they all have a number of closure coefficients, and you'll notice that in the more general models, like before you get to closure, you have double and triple correlations, and they've all been replaced by algebraic expressions involving known turbulence and mean flow properties. And so that's already been kind of done, and you can see that in the paper, the 1988 paper Wilcox, which I think I put on Canvas. And the major coefficients here are alpha, beta, beta star, sigma, sigma star, which are in the K and omega equations. And if we were smart enough, or maybe solutions exist, I don't really know, I'm not smart enough, maybe one of you will be able to one day kind of find closure coefficients more analytically or find solutions to these equations, which hasn't been done. We're still stuck with sort of an inexact theory, which we laid down with dimensional analysis. So what do? We need to find, sorry about that, find closure coefficients that agree with experiment at the end of the day. That's our way of validating. Calibrate these, run our CFD solver, see if it agrees with experiment. The model we're presenting here is interesting because we're trying to do this without experiment based on theory, which I've noted. So first of all, we note that there's beta and beta star in the model, And we're going to try and calibrate these by looking at a decaying, homogeneous, isotropic, turbulent flow. And in those types of flows, there's no mean flow, meaning it's just a stationary field of turbulence. Like if we close the door of the room and turn off the HVAC, you know, we all wave our hands around for a minute and then stop. Eventually the turbulence in the room, there's no like convective effects from the wall temperature, you know, it become homogeneous and isotropic and just start decaying. And if it was high Reynolds number, it'd just be even more intense. If that's the type of flow you like think about when you look at this. So if you make these assumptions here, homogeneous, isotropic, no gradients, no mean flow, then our K and omega equations, let's look at those quick. Right up here, 610 and 69, we can cross out terms, and we will be left with equation 6.16 for K and omega. And you see now, okay, well, I have K, I have omega, and I have unknown coefficients beta naught and beta naught star. Also, these other relations have gone to 0. For this equation to be right, so I have F beta star and F beta equals 1. And it turns out that this little system of equations for homogeneous isotropic turbulence will have a closed form type of solution that obeys K goes as time to the negative beta naught star over beta. Got in my right page, excuse me. Okay, sorry about that. Now, I guess you could try and estimate this with Kolmogorov's theory, but I already mentioned that paper out of Tasagi. And that's the reason I mentioned that paper out of Tasagi. And we know that from those experiments, say of grid turbulence, that K goes as T to the negative N. And they found that N had a range, you know, because that's a measurement. And they found that N goes about 1.25 plus or minus 0.06. And those measurements have been conducted many times by many groups, and they're finding this constant negative power of N for homogeneous isotropic decaying turbulence. So if that value of K must be there, we can take that and estimate 6.17, and we might choose a value to find the ratio. And that would look something like B naught star divided by beta naught of 5/4, which makes sense because 1.25 is about 5/4, I hear. And so that sets one ratio at least for us, which is good. But it doesn't give us all our coefficients, so we need to turn to additional flows. So the next flow that Wilcox decided to look at for calibration was an incompressible constant pressure boundary layer. And if he applied, which sounds pretty familiar because it's the exact boundary layer flow we're solving in Project 4, right? So you can take your K, your omega, and your momentum equation, and then you can write equation 6.18. So this is just like your typical boundary layer flow. And there's a log layer, as you'll see in your predictions and from previous theory. And it turns out that this set of equations has a certain solution, and if you assume the solution in the log layer only, so we just take these equations, we only look in the log layer, we know that the mean velocity should look like the law of the wall. So this goes as u tau divided by kappa times the natural log of the distance from the wall plus a constant, right? So that's just your log law. Right, so if we just draw that to remind you, probably have seen this too much this semester. Got y, we got u, and something like, I guess I drew it the other way, but we'll have a log region. It's straight. And if you impose that velocity profile, you can find k and omega in that region should go as the friction velocity squared divided by beta naught star, and omega friction velocity divided by square root of beta naught star Prandtl constant 0.41 times distance to the wall. So these work in the log layer only. So he's kind of superimposing a solution he knows to be the dominant sort of high Reynolds number log layer of the boundary layer. And from that, he can now see what coefficients satisfy this imposed solution. And it's unique. And he shows that alpha would go as beta naught over beta naught star minus sigma kappa squared divided by the square root of beta naught star. And for this to work, so this is really a constraint. We'll also find that for this to happen, that tau ij is going to be proportional to the friction velocity squared in this region, if you do this. And that means that tau xy, or ij, I'll use them interchangeably here, goes as the square root of beta naught star times k in the log layer. And unfortunately, we're stuck there, so we need measurements of Townsend. You'll see his name a lot in 1976. Shows that the ratio of tau xy to k in this region goes as about 3/10. And I think we mentioned this before, but that was Bradshaw's coefficient, about 3/10. And so in the log layer, based on these experimental observations, we'll set b naught star to be about 9/100 if you put it back in the equations and solve. Now remember, we found earlier that beta naught star over beta naught goes as 5/4. So that means beta naught is equal to 9/125 if you do the math. Okay. Still, we need to find something else. We need to find, I'll do a different color here. These Prandtl numbers. And it looks like if you look in the defect layer, I'll have to go in here, sorry. The choices to match the boundary layer profile, composite profiles that are turbulent, you'll have to choose 1/2. Okay. So looking at equation 620, now that we have some of these coefficients, we have beta naught star, we have sigma. That means we can choose alpha, and evaluating that, you get about 13/25. And so then, based on this simple analysis for the boundary layer and homogeneous, decaying, isotropic turbulence, you'll have this set of closure coefficients. So we found our 5 main closure coefficients really with theory and very basic experiment of Townsend using Bradshaw's coefficient. And those are the ones we presented up when we presented the standard Wilcox model. Now, that's one way of doing things. And it's super simple, super compact, and it actually works really well. This model is very predictive for boundary layers and sort of decaying flows behind grid turbulence. But it has numerical issues. Sometimes it's not stable in the free field. And you might also say, well, what if I take this model and apply it to, say, free shear flows or wakes or backward-facing stops? Guess what? It doesn't work nearly as well. And why? Because these coefficients were chosen only based on these two simplified flows. So you might say, well, other people decided to try and calibrate these coefficients in other ways, and you might say that could be done based on vortex stretching. That's one popular way. Maybe others might be like some kind of length scales. Or jets. Or maybe today you might look at some machine learning techniques, which is in vogue, and time will tell if these ways are successful compared to the traditional ways. Other ways people have thought, here's one in 1986, and when flows are close to separation on boundary layers, they use a different law of the wall, which is summarized here. And so by just using a different law of the wall for separating tight flows or flows near separation, you could have slightly different coefficients. Here's another type of model, Clark. They looked at flows near the center of a channel, and here's empirical relations. So one could use simple empirical relations measurement. So this is how K velocity and friction velocity vary with the middle of a channel. So you could say channel flow. And I'd list others. I guess you could also use LES and DNS databases. I should have mentioned that. And anyway, without going too much detail here, because I don't think it's too important in the big picture, you can find other types of closure coefficients. And with that, I want to make some summaries of K omega, this standard K omega model of Wilcox. I've already mentioned it's excellent for almost all boundary layer flows and modern calibrations, also done by Wilcox almost 10 years later from 1988. In the 1988 timeframe, were across many flows, but then you're a jack of all trades and master of none. It's totally up to us on how we calibrate coefficients. But that being said, the 88 calibration, I would think, is most elegant in general. And that's probably why it's seen as one of the standard K omega models. And what's a better approach in the future for closure, or even choosing which two equation model you have? I think ideally for each closure coefficient or auxiliary relation, one has a unique flow. And even if we use these nice statistical results like homogeneous isotropic turbulence, you're still only finding a ratio or something. So I think to myself, is it possible to choose different flows where we can choose one relation where it's unique and works across all different flows and form a universal turbulence model? Maybe, but not today, and certainly not with these form of the K omega 2 equation model. But I think you'll agree that it's just really remarkable that someone can sit there with no electricity and water in one of the worst wars of our history, and not sure if he has to leave Moscow because the Germans were only a few miles away, and publish this kind of paper. And it impacted people's lives and research, like Wilcox and his followers, for for decades to come. Anyway, it's something to think about. So what we're going to do next time is, now that we've kind of seen the standard K omega model, is Thursday we are going to look at what we call the standard K epsilon model by Launder and Sharma, which is the other most popular two-equation model. So thanks for your time today.